Good morning. Welcome to Memory Management Part 2. I am Nilaran Mukherjee. Today our module objectives will be to understand the fixed partitioning, segmentation, simple paging. Let's understand the scheme fixed partitioning, which is a very basic scheme and building block of the paging. Fixed partitioning is of two types: fixed equal size partitioning and fixed unequal size partitioning. Let's first understand the fixed equal size partitioning. Here it is used in earlier times for small operating system when we have 8-bit system or 16-bit system. The process size was considerably small. Partition size is large enough to fit most of the processes, which ranges from 4 KB, 2 KB, 6 KB, like that. And if not, they at this time they use overlays, which is a concept of executing keeping some of the program in the hard disk and some in the memory, but it is not implemented at the OS end. It has to be implemented by the developer. It requires the compiler support. Each process is loaded into or allocated into only one partition. Thus, process must be small enough to fit in a single partition. Here, in this fixed partitioning scheme, the memory is divided into equal size partitions, and which we can assume. For this example, I am taking a 16-bit system. 16-bit system, that is 2 to the power of 16, 6, 5, 6, 5, 5, 3, 6. So the memory starts at 0 and ends at 6, 5, 5, 3, 5. That is the last address. This is 6 minus 1 will be the last address, and we assume each register is of 16-bit. So we are talking about a 16-bit system. Now it is divided. For our example, we take partition size of 4 KB, that is 1024 into 4, that is 4096, and it is 16 bits. So the first partition will end and the second partition will start at 4096. Similarly, for the second one, it will start at 8192, like that. So these divisions are virtual, made by OS. So OS needs to store the division. How it stores the division? It maintains a partition table, which is a OS maintained data structure applicable for all process. So here we are having a 64 KB memory. This is 64 KB. So 64 by 4. So there will be total 16 partitions. So you can see there are 16 partitions, and every partition will have a start address that is noted at the very beginning, and for all of them the limit is same. So this is a OS maintained data structure, not particular to any process. Now when the new process comes, suppose P1, P2, P3, P4, they are being submitted, they are new process. Now suppose I take OS takes up to, and there is another thing, one OS, so it takes, I am assuming that it is taking up to this, so it is taking partition 0, 1, 2, 3, 4, 5, 6 and 7. So it is taking half of the memory reserved for OS. Now the remaining half, 8, 9, 10, 11, 12, 13, 14 and 15, these are available for user processes. So you can see, as the OS is loaded, status of these partitions are now used and for used, and these partitions are not used, the null means they are available. Now P1 is, suppose it is loaded into partition 8, then P2 will be loaded to second partition, and look here, they are accordingly, this bit is changed. Maybe this is just flipping of 0 to 1. Okay, now accordingly the process will come here and they will be loaded into the partition. Scheme is very simple. Now next thing is to, okay, that the scheme is this. Now we have to consider the logical to physical address mapping. Suppose this is of P1 is currently running. So it starts from here. So we know this is the P1. So P1 is P1 running, and P1 is loaded here in this partition. Now the next point is how to, previously we know that when we have our contiguous memory allocation scheme, we have a PCB. PCB has the base and limit. Here the limit will be the process size. Suppose I am considering this is of 3.2, so limit will be 3.2 KB. That we can easily calculate, that is 1024 into 3.2, it will be at around 33277. So the limit is 3277, and the partition number is where it is loaded. So here partition number value is P1 is loaded at this partition. This one is for P1. In another angle, we can also store the P1, the pre-ID here. Instead of status, we can use PID. So it will be 8. So the PCB of P4, this is the PID. Instead of having base and limit, it will have partition number and limit. So when it runs in the CPU, suppose it generates a logical address of 211. Now P1 is 3.2 kb. So it starts from 0 to 3276 is the last one. So it was trying to address something here. 211. 211, this logical address, if it is not a correct address. Why? If we just directly feed this to MAR, what will happen? We will try to access somewhere here, and that belongs to OS. So we need to access somewhere here. So we need to map from logical address to physical address. Let's see how it is done. First, what happens? We have a partition limit register and relocation register. Partition limit register is for all of the, for this this setup it is fixed 4096, and the relocation register, how to get the value from PID. From the PID I can directly go to the PCB of process 4, where I find the partition number, and OS has a pointer to this table. I go here and I go search by this partition number. So I found 3232768. Now I have to check whether 211 is less than 4096. Yes, it is less than. Then what I have to do? I have to add these two things. So 32768 3278 plus 211, it will be 32979, and this will be the physical address. So you can start searching from the beginning, and it will come somewhere here, and it starts from 32768, because the memory itself does not understand any scheme implemented by OS. Whatever scheme is there, it is virtual to the hardware. That is a software scheme it is. Ultimately, software scheme that what we are using. So whatever is there will be translated to a address that can be physically found. So starting from 0, we get to 32979. So we access the 211 code or data from there, or we write here. So this is the scheme of cert5. If that is greater than, it will be illegal address trap. Otherwise, the MAR will contain the 32979, and which will be accessed. The next algorithm is fixed unequal size. Different unequal partition sizes large enough to fit most of the processor. As we can see, the previous equal version, that is very, it is a limitation, is lot. There can be, suppose when we assume 4 kb, we cannot fit 6 kb, that is greater than 4 kb. And if we have a process of 2.1 kb, there will be a lot of internal memory wastage, which is internal fragmentation. So to fight with that, they came up with a variation which is more flexible. Instead of a single partition size, they allow different partition sizes. So see, if this is, we can allow different size partition sizes: 2 kb, 4 kb, 6 kb, 8 kb, and 8 kb, and 12 kb, and 16 kb. That suppose, as you can see, there are more number of partitions of 8 kb and less number of partitions of other sizes. This may be due to the observation that in the system 8 kb processes are more likely to occur. So that's why we give more number of partition to 8 kb to accommodate 8 kb processes. So if we have a set of processes, we have 2.6 kb, 2.9 kb, 5.6 kb, 7 kb. Now we have two schemes: single queue for all kind of all sizes, or different queue for different sizes. First, we will suppose the new processes we maintain. Here we have, so we will maintain a queue for 2 kb, a queue for 4 kb, a queue for 6 kb, queue for 8 kb, queue for 8 kb, this 2 for a single queue, and this will have another queue, and 16 kb will have another queue. So we have different queues. So you can see here none of the processes are less than 2 kb, so the 2 kb queue will be empty. The 4 kb queue will have p1, p2, p6. p1 is greater than 2 and less than 4, p2 is greater than 2 and less than 4, and p6 is greater than 2 and less than 4. So they will be put in the 4 kb. 6 kb will have only one process, and 8 kb will have a lot amount of processes that will reflect our strategy, and 12 kb will have nothing here, and 16 kb we have two processes, several processes. Now it will be that processes, the first, if we follow first in first out, the p1 will be loaded, then in the 6 kb process p3 will be loaded, and for the 8 kb the p4 and p5 will be loaded. 12 kb will remain empty, and for 16 kb p7 will be loaded. What we observe that here is that some of the queue, as we don't have any processes for 12 kb and no more process for 6 kb, although we have a empty partition, we cannot fit any more processes. This is the empty partition. We have memory, but can't fit any processes to it. This is the disadvantage of maintaining separate queues for separate partition size. So we maintain separate queues for separate partition sizes. So what we observe, the problem here will be some queues will be overloaded and some queues will be empty, leading to wastage of memory. And as we cannot expect that for each size same number of process will be submitted. The next algorithm will be, so I have already explained all of that. So last point was, if only the process which was in 6 got terminated, here also we will be having memory but no one to fit in. So the next concept is to maintain a single queue for all process sizes. So we have a single queue where all the processes are new, ready suspended or new. This midterm scheduler or long-term scheduler. Yes, I am taking the term midterm scheduler in the context that some of these processes can be new or swapped out by the midterm scheduler. So everyone is trying to, either they can be new or already suspended processes. So all of them want to get in, so they are put in a single queue, and they will be allocated to a partition which can accommodate it. So P1 will be here, P2 will be here, P3 will be here, P4 will be here, P5 we can load. Now what we see here, the obvious advantage is no partition is empty. So chance of having an empty partition is lower. Chance of having empty partition is lower. But in the flip side, disadvantage is that we will blindly fit a very small process. We will blindly fit a very small process to a very large partition, you can observe here, and that will lead to huge internal fragmentation. The physical, the logical to physical address mapping will be same as the fixed equal scheme. As you can see, we will just need to here you can see there, in this partitions table we just need to modify it, where every limit was same, we will have different limits here to signify different partitions have different sizes. So that once I get the partition number, I will get the partition start address and corresponding limit. It can be 6144, denoting it is a 6 KB partition. So accordingly there will be 6144 here. Okay, so the mapping scheme will remain the same, only the allocation will change somewhat. So here we can see there will be less chance of having empty partition, because all of them are put into a single queue. We will have most of the partitions will get allocated by some process, but there will be a huge internal fragmentation. The problem with internal fragmentation is external fragmentation can be dealt with compaction, that is moving all the process to one end, freeing up the holes. But here the holes are inside the partition, that is inside P2's address space. So inside this there is a hole, inside this is a hole. So in this scheme, this whatever memory is getting wasted here is can never be collected. Next we go for segmentation. Next we move on to segmentation. Segmentation is a contiguous memory allocation scheme where the process is segmented and different segments are allocated in different holes in the memory. So what they observe that memory is not contiguously available, and doing a compaction from now and then is very time consuming, lots of overhead. So better to break a process into segments, logical segments, and allocate them in a non-contiguous fashion, that is distributed in the holes that are available in the memory. That is the concept behind the scheme. Different segments of a program or process are being loaded into physical memory in different physical address spaces in different places or partitions, allowing physical address space of a process to be non-contiguous. One program in dynamic partition, that is the base scheme. Suppose a process is there, P5, which is of 20.5 kb. So a 20.5 kb process will have, so the process logical address space starts from 0 and it ranges to 20992 minus 1. So this is the logical address space, that is here 1 0 1 2 3 4 5, like this the data or code is there in the process up to this 22091 code or data. This is the logical address space of the process. So first what we do, we divide the logical address space into logically divide it into segments. Suppose these are the segments. So first segment is of 4 kb. So it is now 4096. Then the next segment starts and ends at 46144. Third segments end at 3072 and fifth segment ends at 5120. But actually here the first code of segment 2 had 4096 here Now it becomes 0. The first segment ends at 4095. It would be started at this is the logical address. Now it is mapped to 0 but of segment 2. This is 0 of segment 1. Similarly, this was 6144, the start. This is where it will start, but previously it was 6144 plus 4096, that is 10240 was the start. Now it became 0 but of segment 3. Similarly, this was 13312, but now it has become 0 of segment 4. And the last one has become 3071 instead of 13311. It became 6143 instead of 10239. This will remain the same, 4095. And here the last statement was 18431, but it has now become 5120, and it was 18432, but now it has become 0, the 0th code of segment 5. So the logical address now has changed. The 0 of every segment has a 0th code and the last one of that, and that is 3071. Here it is 5119, the last code. Here it is 2559. Previously it was that, now it has become 0 to 2559, but it has become 0 of segment 5, 2559 of segment 5. So now we see that the process is broken into several segments, and each segment has a starting 0 and end address, which is different from the actual end address if the process actual address, logical address, if the process is not broken. These are all the logical address. Now this, as the process is broken into segment, two question comes. Whenever we have segmentation, first question is how many segments per process, or maximum segment size. Either we can go for choosing how many segments per process or maximum segment size. Both if I fixed, that is, this is 8, and I am talking about a 16-bit system, so my 64 KB memory. So how many I have fixed it? 8. So maximum segment size become 8 KB. If I fixed it here, then maximum number of segment process become 8. Another example, suppose I fixed it to 4 KB segment size, maximum. So maximum number of how many segment per process it will be 64 by 4. So 16 segments per process. For this example, suppose I have considered in this example 12 of 16-bit segmentation scheme. We assume 8 segments per process. So how many bits required? Number of bits required to address segments of a process 2 to the power of 3 equal to 8, that is 3 bits. So we are left with 13 bit. Now when we are having 8 segments, how much maximum segment size? 64 by 8 KB. Now 8 KB is 2 to the power of 10 and 2 to the power of 3. So we have 13 bits required to address a code or data in a segment. That is, we need 13 bits to access the data in a segment. So we have our logical address is now broken into two parts: 3-bit segment number and 13-bit offset. That is, we say displacement within a segment. So the logical address become segment number and displacement or offset, which is of 13-bit in our example, and this is of 3-bit. So now we move forward. Suppose this is the current status of the memory. These are the different segments of different processes that are loaded, and we assume that they are already loaded. These segments of these processes are already loaded. We will, by this example, we will understand how they are loaded. So we have holes here. These are the holes where we can fit in the segments. These segments we can fit in. Now what happens is that previously we have in our contiguous memory allocation for a PCB, but in this we will load these segments into several holes. So if I try to load them in several holes, how it will be loaded? It will be loaded, suppose I load the segment here and load the segment, next segment here, and next two segments one after one here, and the last segment here. So what will happen, that suppose this is the start, and the start is of so we know that this is the 0, and it will 4096, and this is 6144, this is 3072, this is 5120, 02, 023, 02, 02, 02, and this will be 02 2560, everything minus 1, that is the last one. So these are the segment logical addresses. And actual address is of 02 20992, and whatever is 0 here is, this was 8432, and this was 13312, this was the 0th was the 10240, and this was the 4096, and now it has become 0, it has become 0, it has become 0, it has become 0, and it has become 2559, and this is of segment 5, this is of segment 4, this is of segment 3, this is of segment 2, and this is of segment 1. Now if I load it from here, suppose, and this is 10453, where this process ends at 10452, and we have available from here. So I will have a base 10453, then I will have another base, suppose this is suppose this is for example I take it so this is my segment 1 of, and suppose this is P5 and this is P5, and this is segment 2, segment 0, segment 1 are actually the 0th segment, this is segment 2, this is segment 3, this is segment 4, this is segment 5, all of P5. So this, suppose it starts from 8432, so this will end at 8432 plus 4096, so it will end somewhere here 97. Similarly, it is started from 53, and it has started from 40720. Suppose it starts from here, and suppose it starts from 54357. So I will have several base addresses, 8432, then 41720, and limits will be different, 14096, then there will be 61443072. So multiple values I have to store. So this is not the way now, so we cannot go for this. So what we do, we maintain, as every field base and limit has several values, we maintain a separate table for that. So what we have, we maintain a separate table, that is the segment table. As we have using only in this scheme, we are allowing 8 segments per process. So whether or not process uses the 8 segment in its logical address, we will have 8 entries here. And initially when the segments are not loaded, the base is unknown, but the limit of the segment is known. So I have 4096 here, this is the 6144, and this is the this will be 3072, and 6144, then 5120 and 2560. But these are empty, and this, so the logical address space of P5 ranges up to this. To mark that, we will have a valid bit here, signifying these are the valid logical address, and for these entries we will have 0 here. So if somehow it generates 5, we will see first that this is 0, so we will generate a illegal address graph. But if it is generated a segment number 3 in the logical address, we will find this is 1, so we will go for address translation. Otherwise, if it generates 6, 5 or 7, we will find that it is 0, so we will not go for address translation. Instead, we will invoke a illegal address trap. So now when the process are loaded, suppose segment 2 is loaded here, we can load the segments in any hole available, and segment 2 is loaded here, and segment 1 is loaded from here, segment 3 is loaded here, segment 5 is loaded after the segment 3, segment 4 is loaded here. So how to mark that? So segment 2 will start from, that was, we assume that this is 8432, so we will have segment 2, that is segment 2 is this one, this is segment 1 in our case, so 8432. Segment 1, it starts from 10453, so I will have, this is our segment 0 actually, 453. Segment 3 starts from 41720. So this is our segment 3, 41720. Now the segment 5 starts from 41720 plus what is the size of segment 3? 3 kb, 3072. So it will start from 41720 plus 3072. It will start from 44792 and it will end at segment 5 will end at plus 2560. It will end at 47351. That will be the end, and from 5 to there is a hole. And the segment 4 in our example we assume it starts from, so for segment 3 we have to update that this is 44792. For the segment 5 we assume it's segment 4, sorry, this is segment 4. Segment 4, that is our segment 5, 44792, and segment 5 starts from segment 4, that is our 3, will start from 54357. Suppose this is the address, so it will have 54357. So when the long term scheduler or mid term scheduler loads the segments of the process to memory, it updates the fields here, and rest of the field may have garbage value or null value, but as they are 0 they are not considered. And for this field the valid bit is 1, so that means they belong to, up to this belong to the logical address space of P5. Now suppose after that the P5 generates a logical address, so it will be divided into two parts. First one is the segment number, the next one will be the offset. And suppose it generates segment number 2 and it wants to access 4241. So that means segment number 2 means this one, here it is 2, actually this is 0, 1, 2, 3, 4. So segment number 2, and it wants to access a data or write a data here. So actually it is this plus 2, 4, 1, somewhere here it will be, but now it tells that I want to access 2 and 241. But if we are having a contiguous memory allocation, it will say it is trying to access 481. Gross address, logical address. But here it will say I want to access 2 and 241. So how will the address mapping? Logical address to physical address, address mapping will be done is that the PCB, instead of having base values, it will have a pointer to this table. When it generates 2, this pointer will point to the process segment table, and there from 0, 1, 2 we will find that entry. So here, so partition, it will be the limit register, and as we have found that this entry is being asked in the logical address, we will find this is 3072, and from here we will find this is 41720. So first we need to check whether 241 is less than 3072. Yes. If not, we will have a illegal address trap. Otherwise, if yes, we will add these two. So in the MAD, it will be 41720 plus 241. So it will be 16914. So from starting from the beginning, in the memory which does not understand whatever virtual scheme is applied by the operating system, we are giving a sequential address. It will start from the 0 and try to look at somewhere here, and it will access the data from here, which is the 241th instruction after the logical 0 of segment 3. If now it generates another address, let's go for another example. It generates now an address 1 and suppose 537. Let's see how this will be translated. Segment number 1. So you see the logical address in the contiguous memory allocation was a single number. Now it will be broken into two parts. First 3 bits reserved for segment number, the next 13 bits reserved for offset. So the mapping will be like that. So 0, 0, 1 will be the 1 in bit binary bits. So this will be, so when 1 is addressed using this pointer, we will go here, we will find this, and the limit we can fill in from here. And first we will check whether this is 0 or 1. This is 1, so then we will fill it here, otherwise it will be illegal address trap. And we fill here 8432. Then again we will check whether this is less than this. If not, we will add this plus 537. So we will access something of 6998. So it will be somewhere here, we will try to access 8969. So this is how logical to physical will occur in case of segmentation. Hope you understand. If you have any doubt, you can directly mail me, or when the college opens, you can directly contact with me. Next scheme we are going to discuss today is simple paging. Or this is a modification of the fixed equal size partitioning, where we allowed one process to one partition. Here we allow one process different several partitions. That is the simple paging. The first we need to understand what are the pages and what are the frames. Processes are divided. Every process here in the paging, what we have if this is a process, it is divided into equal sized pages, equal sized divisions. Those are called pages. And all the pages has to be loaded to make a process ready. So if the logical address space require n pages, there has to be n memory frames available in the memory. If n memory frames are not available, a process cannot load. Let's understand. So we will take an example of a 16-bit system again, because it is easy to visualize. 16-bit system, that is 2 to the power of 16. We have 64 KB memory. In paging, in segmentation, the first question was what will be the how many segment per process and what is the segment size. Here also the same question we can ask, how many pages per process. That will decide the rest setup. When I say suppose I allow 8, then obviously 8 pages, so page size is 64 by 8, 8 KB. If I say no, I go for 16, then it will be 64 by 16, 4 KB. I can go in the reverse direction. I can say what will be the page size. First I decide on that. So I say I choose page size to be 4 KB. Then I can then going in the reverse direction, I can find number of page per process equal to 64 by 4, 16 pages per process. If I say no, 2 KB page size, then 64 by 2, 32 pages per process. So when the page size diminishes, number of page increases. So page size increases, number of page decreases. Page size decreases, number of page increases. Let's fix our setup here. In our example, let's go for the example. We have having a 16-bit system and memory size of 64 KB. In our example, we assume 2 KB page size and number of page will be therefore 64 by 2, 32 pages per process. So here the logical address space of a process is divided into pages. So pages are logical division of processes, logical address space. Similarly, memory is divided into equal sized partitions, and this the logical division of memory is called frame. One thing we need to remember, that page size equals frame size. So page size equal frame size. So frames are the division of the memory, pages are the division of the process logical address space. You should never get confused about this. Never a question will come on this, that what is the name of logical address division of the process, what is the name of division of the memory. Memory divisions are called frames, process divisions are called pages, but both are of same size. So the main memory will get divided into how many frames? 64 frames. Total 64 frames will be there in the memory. Each of size will be of 2 KB. Size of each frame will be of 2 KB. Now next what will happen is that, suppose we have a new process submitted, which is a new process P5, new or swapped out. So whether it is under LTS or under midterm scheduler. So P5 being 10.3 KB, its logical address starts at 0 and ends at 10,547 is the logical address space of P5. Now it is divided into equal size pages, each of 2 KB. Now we see the first page will take will be consumed entirely, second page also, third page also, fourth page also, fifth page also, and sixth page only from 0 to 307. This much the process takes, rest is empty, and this is called the internal fragmentation. Because page size is fixed here, so in the last page always there will be some free space available in the page where the process does not extend to. So the logical address space of the process covers up to how many pages? 6 pages, because 10.3 by 2 is 5 point something, 5.15 or something. So this will be 6 pages. It will take only 0.15, 15% of the last page will be used by the process in the last page. So the PCB here, similarly these pages will be loaded in different frames here. So every page will have a different base, and every page will have the same limit of 2 KB, that is 2048. So storing multiple values in the base field is not possible, so it will point to here we will maintain a page table for the process. So instead of having a base and limit, here we will have a pointer to the page table stored in the PCB of P1, P5, sorry. So PCB of P5, instead of having a base field, will have a pointer to page table. So it is called PTBR. In the segmentation, it is STBR, segment table base pointer, segment table base register, and it is the page table base register that points to the base address of the page table. And here limit will be the same. This is not of any use to now. Limit is this. Now the page table will have these entries. We will understand this. So it will have entries up to how many. So we have having 2 KB page size. The maximum number of page will be 64 by 2, that is 32. So the last entry will be 31. First entry will be 0, 1, 2, up to 31 entries will be there. 0, 1, 2, 3, 4, 5, then dot 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 up to 31 entries will be there. Among them, how many are used? Initially, when the process is submitted, OS first creates the PCB and creates the page table. And here, as the limit is same for all pages, it is not stored explicitly, but here the valid bit is set. OS divides the process. OS knows how many page it will take. So after dividing, OS found that it takes up to 6 pages. So the logical address space of the process extends to 6 pages. So this will be a valid, this will be valid, this will be valid, this will be valid, up to this they are valid, and rest are all 0. That is, any page number, if the process generates a page number 3, if the valid bit is 1, then the address translation will happen. If the process generates something like 17, it will find there is 0, so address translation will not happen. It will generate a illegal address trap. So we see up to this is the valid logical address space of P5. Up to this is the logical address space. So initially whatever is, nothing will be here, and garbage value is 0, and when the process is loaded, pages get loaded, the value will be filled in here. So now what happens? Suppose we take it has 6 pages, and we consider that it is loaded here. The page 0 is loaded here, page 2 is loaded here, and page 3 is loaded here, page 4 is loaded here, page 5 is loaded here, and page 6 is loaded here. So when the process is loaded by the LTS or MTS, they are allocated to particular frames. Among these frames, the page that is loaded in this frame will consume all the memory in the partition of frame, but in the last it will take somewhat up to this. The rest will be internal fragmentation. So when it is loaded at page 4 here, so we can see the base address will be 4 into 2048. It will start from here. Here it will be 10 into 2048. Here it will be 12 into 2048. Here it will be 15 into 2048. Here it will be 17 into 2048. And here it will be 21 into 2048. So we know where the processes are loaded. So this is page 0 P5, page 1 P5, page 2 P5, page 3 P5, page 4 P5, and this is page 5 of P5. So 6 pages, when they are loaded, the LTS will never forget to update the base address, frame base address here. If it forgets, then it will mark that this page is still not loaded. So LTS never forgets, or NTS never forgets. So when the page is loaded into a frame, the corresponding base address, frame base address, is updated here. Now the problem of segmentation comes here again. Now it has become 0 of page 1, 0 of page 2, 0 of page 3, 0 of page 4. Now how to translate? So here we have a 214. Here we again have a 214. Here we again have a 214. Here again we have a 214. Previously it was the 0, it will be something, it is 40. This 214 will be 4096 plus 214. Now it has become only 214 because it has again started from 0 here. Again it has started from 0 here. Previously it was 6144 plus 214. Now it has become only 214. So the logical address, whatever is generated by the here, will have two parts. First part will be the page number. Second one will be the offset. What is offset? It is the displacement within a page. So a page here is 2 KB. How many pages will allow? That is 32 pages. So how many bits required? 2 to the power of 5. So 5 bits. So 5 bits is reserved for page numbering, and 16 minus 5, 11 bits are reserved for offset addressing. In reverse, we can find that 2 KB, we need to address 2 KB data. Now 2 KB is 2 to the power of 1 into 2 to the power of 10, that is 2 to the power of 11. So we will need 2 to the power of 11, that is 11 bits, to access any data in a page. So here in paging, we have the logical address is broken into two parts: page number and offset. If the total is n bits, we have n bit or m bit page number and n minus m bit offset. That you need to remember. If my page is 4 KB, then how many pages? 64 by 4, 16 pages. Then how many bits required for page numbering? To the power of 4. So 4 bit and 12 bit offset. bit page number and 12-bit offset if page size is 4 KB. Also we can go by 4 KB means 2 to the power of 2 plus 2 into 2 to the power of 10. So we have 12 bits 2 to the power of 12, that is 12 bits offset to address any data within that page, and 4 bits reserved for accessing the page number. Let's see how the address translation is done. Let me erase all the thing. So the scheme is same here. CPU generates the address which is divided into two parts, page number and offset. Suppose CPU it generates the address suppose 317. Directly we cannot go with 317, it is somewhere here, it is in others address space. And look here, you can see that I have intentionally loaded the pages in different frames, although all the frames till now are available, just to signify that as each frame is addressable individually, each page is addressable individually, we can feed them anywhere. You can suppose that these frames are already used, so only these frames were available, and these frames are already used by pages of other process, so we are left with these three frames where we loaded the pages. Now when 347, it will not come with just 347. Suppose it is of 2, page 2 347. So how the address mapping will be done? Using the PCB of the process, OS will go to the page table and find the entry number 2. So it will find the entry number 2, where from and it will find that it is 2048 into 12, that is 24576. Sorry, not here. It will be 24576. Limit is same for everyone, 2048. So first what will happen? A logical address will be generated which will have two parts, page number and offset, same as the segmentation where we have segment number and offset, here the page number and offset. The only difference here is there the segments were of different size, here the segments, here the different partitions are of same size. Another difference is there we were fitting wherever there is a hole large enough to fit that segment. In segmentation, the logical segments of a process were loaded into holes which are large enough to fit them. Here In paging, all pages are of same size. For all process, we have page size is same, of same size. So whenever a process is broken into pages and we have in simple paging we have 6 frames. In single paging we have to have 6 frames, at least 6 frames available in memory, that is 6 free frames, then we can load, then only we can load P5. This is simple paging. The next version will be demand paging. So now let's see how the address mapping will be done. So we had an offset of so what it means that the process wants to access the 3/17th code or instruction or data in its page 2. So it generates the address, OS finds the PCB, goes to the process page table, goes to the entry, finds the frame base address, puts it in the relocation register. Limit is always same. So first they need to check whether this 317 is less than 2048 or not. If no, it will generate a illegal address trap. Otherwise, if it is less than, then the same thing will happen. It will be 317 will be added with 24576 and to generate the physical address. So it will be the 24576 plus 317. It will be 24893. So this address will be fed to memory to locate the data. So it will start from 0 and it will go up to, so it is of page 2. So somewhere here the data will be accessed from here, from frame 12, because we know it is in the frame 12. So this is how the address mapping will be done in simple paging, or in paging this is the same way the address mapping is done. Let's go for another example. So if so this is offset, this is of m bit, here it is 3 bits, and this is n minus m bits, it is 16 minus 5, that is 11 bits, sorry, here it is 5 bits, and total n is 16 bits. So I have a 5-bit page number and 11-bit offset. So suppose it is now trying to access 0 and 114. Again, using the PCB, OS will go to the page table which is maintained by the OS. This page table, PCB, everything is a property of OS itself, not of the process. These are the metadata about the process. So they are maintained by OS. So they reside in the OS address space. Reside inside OS address space. So if that is 0, it will go here and find this is the address 4 into 2048. So it will find the relocation, the frame base address is 8192, limit is always same 2048. It will compare, then it will add 114. So after adding, it will find it is 38306. So it will try to access somewhere from here. So this is how the logical to physical address mapping will happen in simple paging. Hope you have understood. If you have any doubt, you can contact me over mail or when the college reopens. And one more thing, the valid concept of valid bit, I think it is clear now. Valid bit designates up to which the logical address space of the process extends. After that, all the entries for the page table valid bit is set to 0, signifying that they does not belong to the logical address space of the process, and up to this the extent to which the logical address space of the process extends. After that, it is not in the part of the logical address space of P5. Next, we have two more things. So you may see the page. This is the page in the process's logical address space, legal or valid page which are not in the logical address space. Reference to these pages are considered illegal. So they will generate illegal address trap to OS. And there is another one, that is the protection bit we can use, which is here when it's set to 1, that means it is a read-write page. And the read-only pages will have 0, that is any attempt to write on a read-only page will generate a illegal address trap to OS. Next, here we complete the discussion about simple paging. Next, we will cover the topic of translation look aside buffer and demand paging. Thank you.